It got a name. It got tagged with a name 40 years ago. And it's not a great name, but it has stuck. The name is chaos. And these is an example of a chaotic differential equation, or a differential equation, better said, a differential equation exhibiting chaos. And it's an unfortunate terminology because the main point that I'm making about this chaos is that it's not chaos. So if the main point is that it's not chaos, it wasn't a good idea to call it chaos. And there's a lot of misunderstanding about what this means as a technical term. And you will hear people expounding on chaos theory, and they'll tell you that it's complexity of human behavior. You'll hear all kinds of talk, but this is a definite mathematical phenomenon. It is not to be confused with people talking about complex systems or anything like that. It has a definite definition mathematically, and that is aperiodic bounded behavior exhibited by a deterministic differential equation. And I stress the word deterministic there without getting too philosophical. Remember that x prime is a function of x, y, and z. There's no coin flipping there. There's no random output. The change in x is a simple mathematical function of the values of x, y, and z. Same with y, same with z. And we go forward from there. All of the theorems apply. The existence and uniqueness of a solution to this equation is guaranteed by that theorem. This is a completely deterministic system producing aperiodic behavior. And that phenomenon was labeled chaos. And that's what it means. But when we use this word, we mean it in this technical sense, not in the street sense or the politician sense or the whatever sense. This is the mathematical definition of what chaos is. And there's another property that it has. And that is, if you perturb the system, you remember what the attractor looks like. That if you tried doing a little perturbation experiment and perturbed, doesn't matter where, perturbed it right here, move the state point from here to here, what you would see is that the evolution from this point quickly went back into the same region and started repeating exactly the same behavior. In other words, we have here an attractor. And it's obviously not a point attractor. And it's obviously not a limit cycle attractor because it is not a cycle of any kind. It is not a closed loop. This is a new kind of attractor. And at first, people called them strange attractors. And you will see that terminology. They're also called chaotic attractors. And like any attractor, they represent the motion, the stable, as t approaches infinity, motion of the system. And yes, I really am saying that there's a very, very, very complicated geometric object sitting there, and all trajectories are zooming closer and closer to it as t approaches infinity. They are approaching this very complex attractor. So we can now complete that little list that we were making at the beginning, which had form of motion over here and mathematical model over here. And we said that number one was equilibrium, represented by the point attractor. Then the second, more complex form of motion is oscillation. And oscillation is represented by the limit cycle attractor. And now we can say that there is a third form of motion. And that third form of motion is what we have just defined as chaos. And it is mathematically modeled by systems that have chaotic attractors. Now there's a further point, which is this. When we were talking about equilibrium and oscillation, we talked about the transition from equilibrium to oscillation. And we pointed out, indeed we even gave it a name, we called it Hopf bifurcation. And we saw that an equilibrium system can become oscillatory when certain parameters are changed. So the muscle stretch reflex system, which was maintaining an equilibrium, but you start to increase the time delay in the system, and it becomes oscillatory, as in demyelinating diseases. It becomes an oscillatory tremor, and it has changed its behavior from an equilibrium system to an oscillation system, or an oscillatory system. The same thing happens in that case. There are clear examples of a system that is behaving in an absolutely regular oscillation, which, under certain parameter changes, that oscillation is destroyed and is replaced by chaotic attractors. And this is other kinds of bifurcations that we will be talking about. But the important thing is, yes, one and the same system can go from oscillation to chaos. just like one and the same system can go from equilibrium to oscillation when a parameter passes a critical point, a system can go from oscillation to chaos as a parameter passes a critical point. So it's an important lesson to understand that chaos is not a kind of system, it's a kind of behavior which a system may exhibit or may not exhibit, and may be not exhibiting chaotic behavior until a parameter has changed and thereby creates a bifurcation into chaotic behavior. Let me remind you of the examples that we started out with, which was the fluid turbulence example, where it started out in kind of laminar flow, and then we got little vortices, and then there was sort of full-on turbulence there. This is a transition from an equilibrium system to an oscillatory system to a chaotic system. And that's occurring as a parameter is changing in this flow. The other example you saw was an electrocardiogram, which then became irregular. This is an oscillatory system, possibly, that has become chaotic. At least that's a very interesting candidate that we would want to examine, that fibrillation is a form of chaos, and in our own work at UCLA, that's what we demonstrated, that yes, indeed, fibrillation is a form of chaos, and you can find the parameters that shifted the system from the healthy oscillatory regime to the, to the unhealthy chaotic regime. That becomes an important issue when you are trying to do something. We're trying to intervene in these systems. So these are two prime examples of putatively chaotic, potentially chaotic systems in nature, fluid turbulence and cardiac fibrillation, represented by this mathematical model in which an equilibrium or an oscillatory system becomes chaotic. And the question is, what were the magic parameters? And the fact that a given disordered behavior is or is not chaos really matters. Because if it is chaos, then we can find the magic parameters and change them. Now, in the case of cardiac fibrillation, many, many decades, unfortunately, cardiologists tended to take the view that what is fibrillation? It's just a mess. It's just a lot of irregular behavior. The heart becomes desynchronized. It's kind of crazy, and everything goes to hell, and it's irregular. The heart becomes irregular. Well, if that's all you can say about your phenomenon, then there isn't much you can do about it except to do what unfortunately our current therapy is, which is a defibrillator. And what is a defibrillator? A defibrillator is an electrode attached to your heart and taking a lead from a very powerful battery. That output from the battery goes through a capacitor, builds up the charge, and then thousands of volts are delivered to the chest. The patient gets third-degree burns. It's very unpleasant, although you could say it's more pleasant than the alternative, which is that death that ensues within 3 minutes of the onset of fibrillation. But my point is this idea of a massive electrical shock to just reset the whole system, the fact that that's our therapy is a symptom of our cluelessness about the underlying phenomenon. The philosophy here is a bad one. I don't know what's going on there, but I want to blow it away. And so I don't care what's going on. A big enough electrical jolt is going to reset the heart. But that is not a destination therapy for fibrillation. It's kind of the approach of the clueless. I don't know what's going on there, but a big enough bomb is going to blow it away. That's not a happy situation to find ourselves in. And what our research is suggesting is that if you do understand the chaotic nature of fibrillation, and you do understand the parameters that have been changed that move the heart from the good oscillatory state to the bad chaotic state, you can intervene with those parameters in a much less invasive way.